In this video, we're going to look at logarithm properties. So recall that what a logarithm does is it is talking about the exponent. So in other words, it's connected to the exponential equation. In other words, if we have log base b of a is equal to p, that means a is equal to b to the pth power. So we call b the base of the logarithm. We force b to be greater than 0 and b not equal to 1. Otherwise, we don't get very interesting exponential ideas here. So that's what a logarithm does. We've seen that in a previous section. So given a logarithm of base b, again, b is positive and not equal to 1, and any real number p, then if we take log base b of b to a power, we're asking what power do I raise b to get b to that power? The obvious answer is the power itself of p. So this is just equivalent to saying b to the p power is equal to b to the p power. Another way to say this is that if we apply log base b to b to the b power, this log base b and b to the exponent cancel each other out, and it just gives me back the exponent. Knowing that tells me log base b of b would have to be equal to 1 because b is b to the first power. And log base b of 1 is 0 because 1 is b to the 0th power. As long as my base is positive, not equal to 1, b to the 0th power is 1. So we get these properties of logarithms from its connection to exponents. Let's do some calculations, and we'll quickly go through these calculations and show you how it's done. In the first case, since the base of the logarithm is the same as the base of the exponent here, so base 3, we get out a 7. That's pretty straightforward. Log base 2 of 8 to the 6th power can be rewritten as log base 2 of 2 to the 3rd raised to the 6th power. In other words, we can rewrite 8 as 2 to the 3rd, raise that to the 6th power. Using the rules of exponents, that's log base 2 of 2 to the 18th power, which is going to be equal to 18. Having the ability to rewrite 8 as 2 to the 3rd and then use rules of exponents allows us to solve a problem like that. Natural log of e to the 5th, that's straightforward. Natural log is the log base e. Therefore, I get a 5. And then log base 9 of 1 is going to be 0. 9 to the 0th power is equal to 1. So that's how we can use those rules of the interaction between log base b and b to a power. So this is what we kind of refer to as the log an exponent inverse property. If we have base b greater than 0, b not equal to 1, and any real number x, then log base b of b to that power is equal to the power itself. So the log undoes the exponent. And it actually works in reverse as well. So if I have b raised to the log base b of x power, I get x for the exact same reason. So let's do some more examples where I go both ways. Obviously, this first one is moving the same way we did before, and then these others are the reverse. Go ahead and push pause on the video if you'd like to try these on your own. In a couple of seconds, I'll show you how each is done. All right, so natural log of e to the 12th, that's just like the previous ones we were doing. Natural log and e cancel each other out, and we just get the exponent of 12. Similarly, if I take e to the natural log of 4.85, I'm going to get 4.85. Oop, the decimal should be there. If I take 10 to the power log of negative 2.1, now this is an interesting thing. If I take log of negative 2.1, I get a non-real number. So be careful about this. The inputs of the log function have to be positive. That's with any base, including the base of 10 that we have here. I used base of 10 because that's one of the bases that we have on our calculator. So you can check this very easily by just typing in log of negative 2.1. Inside the argument, we have a negative number, so this does not exist. Now, by the way, interestingly enough, if we had a negative 12 up here, it would have been all right to have a negative 12 because e to the negative 12th power is still a positive number. It's a very small positive number, but it's positive nonetheless. So you can test this one out if you'd like. It's okay to have a negative in the exponent, but it's not okay to have a negative in the argument. Now, if we have any positive number in the argument, then we're perfectly fine. Here we get a 5.9. Now, I explained earlier why this is true, why when we take a log base b of b to a power, it's equal to that power. We can also use a very similar logic to say that what this is doing. The reason this works is if I take log base 7 of 5.9, let's set that equal to a numerical value, which I'll just call z. Using the rules of exponents, that means that 7 to the z power is equal to 5.9. So this power is the power where if I take 7 to that power, I get a 5.9. Just replacing the z with what it's equivalent to, which is log base 7 of 5.9, gives me this equation. So z is the log of 7 of 5.9 equaling z. means 7 to the z power is 5.9. We said z is equal to this, and therefore we get this equation. Hopefully that makes sense. So this exponent logarithm inverse property is very important, and it shows us what's going on. Remember, in this second equation, for this to work, we just said x has to be greater than 0. So x has to be positive for this to work because you can't plug in a negative number into the argument of log base b. But as long as we have x greater than 0, we have it this equation, we have this identity for any x value. Those are very important properties of logarithms, but they're not the only properties of logarithms. Here's another property for logarithms. This is called the product rule for logarithms. Given a logarithm with base b, I have obviously positive b not equal to 1, and two positive real numbers, then log base b of the product of m times n is equal to log base b of m plus log base b of n. This is a very interesting property because it doesn't work the way maybe a lot of people expect it to. The reason it doesn't work the way people expect it to is because this actually comes from rules of exponents. I'll show you where this product rule comes from, and then hopefully it'll make sense. And then we'll go ahead and look at some other rules after that. So because m and n are both positive, I can write those each as b to a power. I'll write m as b to the w power and n as b to the z power. So that means log of the product of m and n is going to be log, again, this is log base b, of b to the w power multiplied times b to the z power. Well, we can use the rules of exponents and say that is actually log base b of b to the w plus z power. Using the exponential and logarithm inverse property, we know that that is actually just the exponent of w plus z. Log base b of b to an exponent is just the exponent itself, so that's w plus z. But we also know that w is log base b of b to the w power because of the exponent and log inverse property, plus z is log base b of b to the z power using that property. And this is log base b of m plus log base b of n. So we get log base b of m plus log base b of n. So there you go. Log base b of the product of m times n is the same thing as log base b of m plus log base b of n. And that basically came from our rule of exponents that say if you take b to the w times b to the z, you get b to the w plus z, along with the rule of exponent logarithm inverse. If I take log base b of b to an exponent, I get the exponent back. We can use that a couple of times. So that's what we get. So this shows that the product rule for logarithms is coming from essentially the product rule of exponents. In a similar way, where there is a quotient rule for logarithms that says log base b of m divided by n is equal to log base b of m minus log base b of n. So that gives us a rule for dividing two numbers inside the argument of log base b. Now our two numbers, just like before, the m and the n have to both be positive for this to work. Otherwise, this does not hold true. If these are negative, then this is not a real number. Log base b of the negative number won't be a real number. Another rule that we get with logarithms is called a power rule for logarithms. This says if I take log base b of m to any power, I can pull that power out front and multiply the power times log base b of m. So this gives me something to do with an exponential function even when the bases don't match up. Log base b of m to a power is equal to that power times log base b of m. Just like I did with the product rule, I'm going to show you where the quotient rule and the power rule come from of logarithms. So we saw where the product rule came from. It came from letting m equal to b to some power, we called it w, and n equal to b to the z power. With the quotient rule, I do the exact same thing. I let m be b to the w and n be b to the z power. Then log base b of m divided by n is going to be log base b of w divided by divided by b to the z power. Let me rephrase that. So this log base b of m divided by n is going to be equal to log base b of the argument b to the w power divided by b to the z power. M is equal to b to the w, n is equal to b to the z. Well, using the quotient rule of exponents, b to the w divided by b to the z is b to the w minus z power. The exponent logarithm inverse property says that this becomes the exponent w minus z. And we know through the log exponent inverse property, w is the same thing as log base b of b to the w. Z is the same thing as log base b of b to the z. Log base b of b to the w is log base b of m. Log base b of b to the z power is log base b of n. And that's how the quotient rule of logarithms works. So log base b of m divided by n has to be log base b of m minus log base b of n. In a similar way, the power rule works. The power rule says this, power rule of logarithms. So we'll once again let m be b to the w. So log base b of m to the p power is log base b of bw all raised to the p power. The power rule of exponents says this is going to be b to the w times p or p times w. Either way, order doesn't matter there. The exponent logarithm inverse property says we can just pull off the exponent. That becomes a p times w. We know that w is log base b of b to the w power. So we replace w with this. And that is log base b of b, log base b of m, which shows the power rule. The power rule says log base b of m to the p power is p times log base b of m. These three rules are really nice to have, and notice they all rely, showing that they all work, all relies on that exponent logarithm inverse property, both in this step and also in this step. Let's go ahead and play around with these rules. First, let's rewrite an expression as a single logarithm. Now, in these cases, I don't know what b is, so I can't actually calculate log base b of 82 because I don't know what b is. Same thing with any other number. I don't know what b is, so I can't calculate log base b of a number, but I can rewrite the expression as a single logarithm. So let's go ahead and do that. All right. So this one, since we have log base b of a number plus log base b of a number, I go back up. That's the right-hand side of the product rule. If I want to rewrite this as one expression, I can just take log base b of the product of those two numbers. So this is going to be equal to the log base b of 82 multiplied times 12. So as a single expression, that's log base b of 984. Again, that's just a straightforward application of the product rule. In this next example, that's a straightforward application of the quotient rule. So using the quotient rule, this is log base b of 240 minus log base b of 15. I'm going to get log base b of 240 divided by 15 in the argument. 240 divided by 15 is actually the number 16. So that is log base b of 16. Again, that's a straightforward application of the quotient rule. I'm using the quotient rule to go from first to this second one. Product rule to go to this first one to this second one. Now we may think, why would we ever want to rewrite two logs into one? Well, it turns out that that's important with solving equations involving logarithms. So we're going to have logarithms and we're going to solve equations using logarithms, or excuse me, solve equations with logarithms in them. If we have multiple logarithms, we're going to have to combine them into a single expression. At least sometimes we will. So this is an important thing to know if we want to solve logarithm equations. So let's do the rewrite thing. But now, instead of having numerical values only in my arguments, let's actually have expressions that involve the variable x in my arguments. Go ahead and push pause on the video and try this on your own. In a couple of seconds, I will show you how each problem is done. All right, so now we have variables inside the argument of our logarithm. And what we're going to do in the first case, since this is log plus log with the same base, by the way, make sure everything has the same base. Otherwise, the product rule, the quotient rule, and the power rule don't work. So we do need the same base on the product and quotient rule. I guess there's only one log for the power rule, but with the product and quotient rule, we need the same base. If we have that, then we can multiply. We can take 9x to the fifth multiplied times 5x in the argument of our log base b. And so that's going to give me log base b of 45 times x to the sixth power. So that's how I rewrite that as a single logarithm. In this case, this is going to be the quotient rule because we're subtracting. That means inside this argument, I'd have 9x to the fifth, and I divide that whole thing by 5x. So I get log base b of 9/5 times x to the fourth. If you want to rewrite 9/5, you can. You can rewrite 9/5 as 1.8 if you'd like. But that's the idea. So here we use the product rule. Here we use the quotient rule, and we had a variable inside of our argument. And this helps us out later when we're trying to solve logarithm equations or equations with logarithms. Let's do another rewrite. Let's take 4 log base b of 5 and 3 log base b of 4x to the fifth and do a rewrite as a single log base b of a single argument. Both of these involve the power rule. If you want to try these on your own, push pause on the video. In a couple of seconds, I'll show you how to do each of these on the screen. All right, this first one, power rule says this is going to be log base b of 5 to the fourth power. 5 to the fourth power is 625. So we get log base b of 625. With this second problem, it's very important that when we raise the argument to the third power, we're not just raising x to the fifth to the third power. We're raising the entire argument of 4x to the fifth, all to the third power. So I need to make sure that I raise 4 to the third power. That would be 64. And then also x to the fifth to the third power. That would be x to the 15th using rules of exponents. So be careful about that. Oftentimes, especially in the reverse way, people will just take the 15 out front and forget about the 64. and that's not correct. So like I had a previous problem that said log base b of 45x to the sixth, that is not the same thing as 6 times 45, 6 times log base b of 45x. I can't do that. I have to take the entire argument raised to a power and then take that power outside if I want to take a power outside. Same thing. And here, when I take the argument to the third power, I need the entire argument inside of that log to be raised to the third power. So that's how we use the power rule. So the previous three examples, examples 3, 4, and 5, were examples that we need to do and we need to know in order to solve equations with logarithms in them. Now what we can kind of do is do the reverse. Let's evaluate expressions if we know certain values. If I know that log base b of x is 4 and log base b of y is 10, without knowing the x, without knowing what the value of b is, without knowing the value of x, I can still calculate things like log base b of x times y. And I can calculate things like log base b of x to the fifth. If you want to try to do these two on your own, go ahead. In a couple of seconds, I will show you how these are done on this video. These types of problems, like I said, are kind of the reverse of what we just did because we start with a single logarithm and now we want to break it up into its parts so that I can replace a log base b of x with a 4 and a log base b of y with a 10. In this first example, we want to break this up into log base b of x plus log base b of y because that's the product rule. Now I know each of these values. Log base b of x is 4. Log base b of y is 10. That means log base b of x times y is equal to 14. There's other ways you could have gone about doing that, but that I think is the most straightforward. Similarly, if I'm in this situation, what I would do is I would say this is argument x to the fifth. I can say, using the power rule, that that is 5 times log base b of x. I know that log base b of x is the number 4, so that is 5 multiplied times 4, which is 20. Therefore, I can evaluate these expressions if I know log base b of x and log base b of y. I do that by breaking it up using in this case, I used the product rule. In this case, I used the power rule. I can always mix up lots of the different rules and see what's going on. Mixing up different rules and trying to see what's going on is exactly what example 7 is going to ask us to do. We have log base b of x to the third divided by y squared, and then log base b of x to the third times b to the 7th power. Go ahead and push pause on the video and try this on your own. In a couple of seconds, I will show you how it's done on this video. Now, again, we're starting with log base b of x is 4 and log base b of y is 10. So I need to break these things down into something where I have log base b of x, something where I have log base b of y. The first step in this first problem is to say that is a division. So we can write this or rewrite this using the quotient rule. The quotient rule says that's log base b of x to the third minus log base b of y squared. Each of those individually, we can apply a power rule to. In the first case, that's going to come out as 3 times log base b of x. In the second part, that's going to come out to 2 times log base b of y. That's just 3 times the number 4, since log base b of x is the number 4, minus 2 times the number 10, since log base b of y is equal to 10. That's going to give me 12 minus 20, which is a negative 8. So just by knowing log base b of x and log base b of y, I found out that log base b of this expression x to the third divided by y squared is equal to negative 8. We can do a very similar thing if one of our variables is not y, but rather b. So here we'd start out by using the product rule. This is log base b of x to the third plus log base b of b to the seventh. In the first part of that expression, I would use a power rule. That would give me 3 times log base b of x. The second part of that expression, since I have base b on the logarithm and base b on the exponential, those are going to cancel each other out using the exponential logarithm inverse property, and I just get the number 7. Log base b of b to the 7th is just b to the 7th. Again, that only works because I have the same base on the logarithm and the exponential. Log base b of x is 4, so that means this is 3 times the number 4 and then plus 7. That's going to be 12 plus 7, which is equal to 19. So in this case, just knowing log base b of x allowed me to calculate log base b of x to the third times b to the 7th. In example 7 and in example 6, we saw that we can evaluate log base b of a more complicated argument as long as I know log base b of the simpler arguments, log base b of x, log base b of y. When I multiply x and y, I can find log base b of x times y. I can find log base b of x to the 5th. I can find log base b of x to the third divided by y squared. I can find log base b of x to the third times b to the 7th. So if I know log base b of x, log base b of y, then I know log base b of more complicated arguments. Now, one last rule that we're going to have in this section is the change of base rule for logarithms. We're going to have two bases, one of which is base B, like we've been using before, and the other is going to be base A. Now, for both bases, we want them positive and not equal to 1 for this rule to work. But if it's the case that both of our bases are positive and not equal to 1, then if I can calculate log base b of x, then I can calculate log base b of x, and it's going to be the same thing as log base a of x divided by log base a of b for any positive real number x. So this is called the change of base rule for logarithms. And this allows me to do a lot of calculations with logs using an efficient way on our calculator. Because our calculator has log base e, which is the natural log, it also has log base 10, which is the LOG button on the calculator. So if I have log base 7 or log base 2 or log base 1.05, I can either use log or the natural log on our calculator and a change of base rule to calculate whatever that logarithm is. So this is a very important property of logarithms, the change of base rule. Now, before we actually use this, I want to show you why the change of base rule works. By the way, this is also called the change of base property in other books. So you can use change of base rule, change of base property for logarithms. So this is what it says, but why is that? Well, think about log base b of x. Let's call that some new letter. We'll call it a z. So log base b of x is equal to z. That means b raised to the z power would have to be equal to x. At this point, we can apply log base a to both sides of this equation. If I take log base a of the left side, I get log base a of b to the z. And on the right side, I'd get log base a of x. On the left-hand side, this exponent of z can be pulled out front utilizing the power rule of logarithms. So the z can be brought out front, and I get z multiplied times log base a of b is equal to log base a of x. Now, dividing both sides by log base a of b gives me log base a of x divided by log base a of b. But what was z? Well, z was just log base b of x, so this tells me log base b of x has to be equal to log base a of x divided by log base a of b. So that's exactly what the change of base rule says. And now that we know where this comes from, we can use it freely. Let's use the change of base rule and the calculator to calculate log base 3 of 14, log base 7 of 90, and log base 7 of 0.5. If you want to try these on your own using the change of base property or the change of base rule, then you can. In a couple of seconds, I will show you how each of these is done. So if I want to use the change of base rule and the calculator to do this, my calculator has both log base 10 and the natural log. It turns out I can use either of those. I can use log base 10 of 14, and then divide that by log base 10 of 3. On the calculator, that's just log of 14 and then log of 3. You get about 2.40, so you get approximately 2.40. And if you took that exact number, not the rounded number, but if you took the exact number and you took 3 to that power, I'll write down all of the decimals on my calculator, even though this is not, a lot of times on my calculator, I would write 3 to the ANS, that's 3 to the answer that I got. You would end up with 14. So whatever this numerical value was, exactly, if I take 3 to that numerical value, I should get a 14. Okay. So that's what that means. Now, if I had wanted to, I could have also utilized natural log instead of log base 10. So if I want to do natural log of 14 divided by natural log of 3, I'll get this exact same value. And when I get that value out, I can check that it's the right value by seeing that 3 raised to that, that specific value gives me 14. Again, not the rounded version, but the specific unrounded version would give me 14. So that's how I can use my change of base rule with my calculator to calculate log with any base and of any number. And this is really nice because normally I don't know what I don't know what power to raise 3 to give me a 14. How about the next one? Well, the next one, I'll use natural log. You could have used log base 10 as well, but natural log of 90 divided by natural log of 7. That's what I'd plug into my calculator. This is not going to be a whole number. So it's going to I'm going to write down an approximate answer, and the calculator gives me back an approximate answer of about 2.31. Again, if I took the exact answer, what this is meaning is it's saying that 7 to the roughly 2.31, or on my calculator, I got 2.312444731. So 7 to that power is about 90. Okay. So even this number, though, is a rounded number. So be careful when you're using that. In this case, where I take log base 7 of 0.5, again, I'll use natural log, but you could use log base 10. They both come out to the same thing, always. The quotient rule works with any base. So we do natural log of 0.5 divided by natural log of 7. When I do that on my calculator, I end up with a negative 0.36 if I round to 2 decimal places. Let me just signify that that is rounded. And again, that means if I take 7 raised to the negative 0.3562071 number, then I'd get right about 0.5. So that's what we're saying. Okay. So this shows you how you can calculate log base any number of any number in our argument. As long as the number in our argument is positive, then we're good to go. Because if we get 0 or a negative number in our argument, then that log doesn't exist. As long as I have base that's positive and argument that's positive, then it works just fine. This rule even works for bases which are not whole numbers. Most of the bases that we've been dealing with so far have been whole numbers, but we could have bases like 1.05, and this rule would still work. We could still use the change of base rule in our calculator to calculate log base 1.05 of 2, or log base 1.05 of 0.12, or log base 1.05 of 100. All of these can be done using a change of base rule. Go ahead and push pause on the video and try these if you'd like. In a couple of seconds, I will show you how to do these on the video. All right, let's go ahead and do these. Again, it doesn't matter if you use base 10 or the natural log on the calculator. We're going to take log of 2 divided by log of 1.05. Now this is log base 10 on my calculator. You could have also used natural log of 2 divided by natural log of 1.05. I get right about 14.21. Again, that means 1.05 raised to the 14.21 power gives you about 2. In the same way, if I take log or natural log of 0.12 and divide it by natural log of 1.05, I will get log base 1.05 of 0.12. And when I do that, I get a negative 43.46. That's rounded to 2 decimal places. Again, that means 1.05 to that negative 43.46 power gives you about 0.12. And lastly, one log base 1.05 of 100. I could either take log base 10 of 100 and divide it by log base 10 of 1.05. Or I could take natural log of 100 divided by natural log of 1.05. And that would give me 94.39. Roughly. That's obviously rounded to 2 decimal places. And that means 1.05 to the 94.39 power, roughly, is going to give me about 100. Again, I'm rounding everything to 2 decimal places here to make things easier. But there you go. That's how we can use that change of base rule in order to calculate log of any base of any argument, as long as our base is greater than 0, not 1, as long as our argument is positive. We see that the change of base rule allows me to calculate log base b of x for any b and any x that makes sense. I do want to mention that some calculators, like the TI-84, can calculate this directly. Some places in the calculator, there's a log where you can pick out any base that you want. So there's a feature on a TI-84 that'll calculate log base any b that you want of x. And so you can actually use that calculation on the calculator to confirm all of these ones that we did earlier. So for instance, if we were here trying to calculate the log base 7 of 90, we did it using the change of base rule earlier, and we got about 2.31. But if you had a calculator that could just take log base 7 of 90, you would have also gotten that number, which is about 2.31, more specifically about 2.312444731. So you could have done this directly if your calculator has a feature that does that directly. There'll be an added video that shows you how to do log calculations, and on the TI-84, if you have a TI-84, you can reference that video either using the change of base formula or directly taking log base 7 of 90. I just wanted to mention that because change of base is not the only way that our calculator can calculate log base b of x if we have a nice graphing calculator. So in this section, we saw a lot of tools used to simplify and rewrite logarithms and expressions with logarithms in them. In the next section, we'll use those tools to start solving equations, both logarithm equations and exponential equations.